So let's start off our study with two-dimensional kinematics with just two thinking questions first, right? So hopefully you've got a chance to try think about this on your own, but let's talk about them, right? So imagine you have a train going through a tunnel, okay? So there's probably a mountain over here, and you have let's say a train, and it has a launcher on top. So you put a launcher on top and you put a ball, right? The train is going to move at a constant speed, all right? So it doesn't matter really what it is, maybe 60 miles per hour, 100 miles per hour, it's a speeding train straight through. And you have a ball and you're going to launch that straight up, okay? So you can do that, right? You're on, let's say you're, if you're on a train speeding through, just toss a ball straight up, all right? So the train is going to go straight through the tunnel, and after a certain amount of time, it's going to be here like that. And now what will happen to the ball? Let's say you have launched it high enough that it will crest the mountain. It'll be tall enough so it doesn't hit the top of the mountain. Now there's a couple of options. Will it come straight back down if you throw it out upwards, so it just goes up and go down? Will it actually go forward? And will it land before the train when it comes back down? Will it land exactly where it started? Will it land after the train because you're starting some momentum, or will it actually go back? Okay, which one will that happen? Right. Another question is, while you're thinking about that, if you're on a cliff, let's say, right, or on top of a building, whatever, and you kick a ball, right? So this is you, right? You kick, just running over, kicking a ball straight through horizontally. Okay, you're just kicking it horizontally, and at the same time, compared to someone who takes the same ball and just drop it at rest. Okay, so when you drop it at rest, it will come down. If you kick it forward, you'll probably follow a path something like this, right? Which one will land on the floor first? Okay, now I remember probably when I was at a very young age, even I know nothing about physics. In fact, even in high school, I was really bad at physics and I never liked it. But still, I remember just even before that, there were two things about now I know that this is part of physics or what physics studies. There are two particular phenomena that really intrigued me. And one is what we discussed already. It's different massive objects actually fall at the same rate. That really was one of the most mind-boggling thing. And this is the second, right? The first one is, like we said, like whether it's a small a marble or a tennis ball, or even if I drop a house, all of them actually fall at the same time, independent on how massive and how heavy that object is, right? So and the second thing is this. If you launch it, if things are moving at constant speed, and if you launch it, the correct answer is this one. It lands exactly back on the train, even though if it passes a tunnel, that doesn't matter, nothing changes. Basically, whatever, whenever, if you move, as long as you're moving at constant speed and you launch something straight up, it will basically land right back at the same place. So how do we analyze that? What's going on? We'll see that in a second. And it's more apparent in this example. So now what happens is I can actually draw the velocity vector at every single point. Okay, so at first you're kicking it, so you have an initial velocity that way. And if it follows this path, it means that the velocity sort of tells you which way it's going, right? So it's going this way, it's going this way, it's going this way. So it does change as it goes down. But remember, vectors has two components. So every vector over here, let's say V, is made out of, I'll use a thicker arrow like this, or thicker arrowhead like this, Vx and Vy, right? At every point, I can resolve it into the X component and the Y component, like that. And one of the biggest principle or the biggest takeaway before we start on all the mathematics is this. This is the only physics concept there is about this lecture, right? The rest is just mathematics. And the concept is this. The X and Y components evolve independently. whatever you do with the x component, it does not affect the y component. So so we can explain this phenomena, why they will actually land at the same time. For this object, you only have a y component, vy. It's not good to reuse the same variable when they represent different numbers, but I have too many too many arrows to make them 1, 2, 3, 4. So let me take the liberty to abuse that rule a little bit, right? So this one falls with a certain vy. This one also falls with certain vy. And the fact that you introduce the x direction motion over here has completely no effect on its y velocity. So its y velocity will fall faster and faster. Just like this will fall faster and faster. It's not a constant speed because it does accelerate. Remember, everything accelerates at minus g. If I'm using this as positive, for example, if you turning the other way around, then a is positive g, whatever, depends on your system. But yeah, so they do, vy, the y component of these velocities do increase. I probably should draw this as smaller. You can sort of just tell, not the best drawing. Over here, there's no vy, there's a little bit of vy, there's more vy, there's more vy, like that, right? So the vy component does increase. So it actually does change the speed. It gets faster and faster as it goes down. However, the x direction, the fact that you introduced a kick, horizontal kick like this, it will completely not affect the y direction. Okay, same thing over here. What we have done is basically this is just double of that. Right? If I take this whole thing and mirror it, I'll have a complete arc, a complete upside down U-shape arc, right? It's called parabola. Yeah, so the fact that I throw it straight up, if the train is not moving, you understand it will go up and down, right? If the train is not moving. The fact that it's going in constant velocity, what it does is basically when you shoot it up, not only have you actually introduced the upwards velocity, you have also introduced a Vx component. So you have introduced a Vy and a Vx, okay? But since Vx is constant, but since during the air motion, nothing actually changes Vx, right? And the train is moving at constant velocity, so the ball's Vx will also move at the same Vx velocity of the train. So the fact that you introduce a Vy component has no effect on Vx. So if the ball never get launched, it will stay over here. So after a certain amount of time, let's say it takes 10 seconds to go through to the other side, if you do not launch it at all, of course the ball will stay right here, right? Stay on top of the train. The fact that you introduce the Vy does not change the fact that when it comes back down, it will be there, okay? All right, so a little more analysis is we can go one level deeper is we can take a different color pen and draw the free body diagram of that path, right? So let's say as the train moves, right, when the train is somewhere in the middle, the ball is also somewhere here or here at different times, right? Let's draw the free body diagram at these different times. At this time, what are the forces on it? All right, so let's assume the ball is heavy enough that the air resistance has very, very negligible effect on it. It's small enough, it's dense enough, it's heavy enough. Right? So over here, what is it in contact with? Nothing, right? So it's not in contact with anything. So there's no contact force anywhere through here. Throughout the path, there might be a force to launch it. So at this moment, there is a force because it's in contact with whatever the launcher is. It might be a spring, it might be a compressed air gun or whatever, right? It's in contact with something, but the moment it left, the immediate instant it left the launcher, there's no more contact to anything. So there's no contact force. And the only non-contact force is gravity, which always acts on it, right? Right, so you have its weight, okay? And what is the weight? Well, we have a formula for that. We know that it's mg, right? And since its mass never changes, unless it gets less and less massive, it's losing mass for some reason. So its mass doesn't change. Then g is also a constant, so its weight never changes. So the force does not change, and the force only affects the y direction. Again, it does not affect the x direction. So if it starts off with a certain Vx, it stays, the x component, the Vx component is basically constant. And if it's constant, let's say it is 5 meters per second, and if the train is also moving at 5 meters per second, guess what? They will have to land at the same place, all right? I'll see if I have, due to sort of limited resources in my office, I'll see if I can do an experiment with this. If not, I'll see if you can, I can find some good videos that show you exactly this experiment. And but even more interestingly, I want you to see if you can try this yourself. Actually, that is actually possible to try. You can take an eraser or something on the edge of a table, take two objects of identical if possible, and put it at the edge of a table, and with one hand try to flick that and sort of just horizontally flick that off the table. The other hand drop that vertically from rest at the same time, and see how they land on the ground. And you can give that a try yourself. All right. So we'll move on to the look at how do we analyze this qualitative picture quantitatively.